In this brief video, we'll take a look at how to use the graphing calculator to graphically zoom and solve equations that might be difficult, if not impossible, to solve by hand. And the example we're going to work with is this one, x to the fourth minus 3 equal to 2x minus 1. You could imagine trying to rearrange things and do some factoring, but with the fourth power there, that's probably going to be beyond most of us unless we happen to get rather lucky. So we're going to take a look at how to use the calculator to get a handle on these solutions. And what we're going to do is graph the two sides of the equation as separate functions. And so I'll hit the y equals button, and I will enter x to the fourth minus 3 as y1. I'll enter 2x minus 1 as y2. And of course, when we graph these, we're going to expect to see a sort of a U-shaped thing, not unlike a parabola, but geometrically different from a parabola. And of course, a line with y-intercept -1 and slope 2. So I'll go zoom 6, which puts us in the standard window, -10 to 10, in both the x direction and the y direction. And as we look at the graph evolving, we see that there are going to be two intersections of the two curves. One in the third quadrant, roughly in the neighborhood of x equals -1, and one in the first quadrant, somewhere it looks like between x equals 1 and x equals 2. So the way we're going to go about this is to zoom in around each of the intersections. So I'm going to hit the zoom button, which is the very top middle button, and choose the first choice, Z-box. And when I do that, I get a tiny little cursor which starts at the origin, and if I scoot it around using the arrow buttons, I can kind of separate it there from the rest of the picture and see where it is. What I want to do is make a little box around the first intersection point down here where that U-shaped graph and that line come close to one another. And so I'll position my cursor in one corner of an imaginary little box that surrounds that. I'll press Enter once, and then I'll continue using the arrows to open up a little box, and it'll sort of follow the diagonally opposite corner from the corner I've already selected. And if I hit Enter, it'll take the contents of that box and blow them up to fill the screen. And so here is kind of a zoomed in version of that first point of intersection. If I now hit the Trace button, I can scoot the cursor over to where those curves are intersecting, and I see that it's at x equals about -0.801. If I click one to the right, it's about x equals -0.79, and so it's changed by less than 100th as I click from one pixel to the next, which means that's about the precision that I'm getting as I look at the trace here. If I wanted to get an even better handle on the solution, I could zoom one more time. I could hit zoom and then the zoom box, and I could do what we just did before. So I'll scoot to one corner of a little box, hit Enter, scoot my cursor to the other corner, and hit Enter again and blow that up some more. And now if I'm tracing, as I look at the x coordinates of these points, as I click from pixel to pixel, I've got about -0.7957, -0.796. I'm tracing by roughly 1,000th each time. So if I get right here on what looks like the intersection, I can probably be fairly confident that's good to at least two places. So I'm going to say that one solution to this equation is x equals -0.80, which is what I get when I round it back to the second decimal place, back to the hundredths. Now, there was another point of intersection. What am I going to do about that? Well, I'll hit Window, and I'll go back to the original window, which was -10 to 10 in both directions. I also could do zoom 6 as I did previously. And this will give me the original window. And there are the graphs, and I can just go to the other point of intersection and zoom in on that, see what its x coordinates. So I will hit zoom and box, and work my way over here. Little box around that intersection. And maybe do it one more time. So there's zoom and Z box, and second time. And now graph unfold, and if I trace, I should be tracing by a pretty small amount. So there's 1.500, 1.499. Still, to the nearest 3 places, 1.499. So this is certainly good to 2 places, probably good to 3 places. So I'm going to say that's 1.49. If we had wanted greater precision, if we had wanted to be able to rely on more decimal places, we could have just kept zooming until we got the desired precision. Another approach that is pretty much equivalent to this is to do a little simplifying. So I could, let's say, subtract 2x from both sides of my original equation and add 1. And I would get basically everything to one side. I'd have a 0 on the other side. And I could graph this as a single equation, x to the 4th minus 2x minus 2. And in that case, I would be looking for places where its value was 0, or graphically places where it crossed the x-axis. So these are x-intercepts, or zeros. And I'm going to claim that if you graph this single function and look for its x-intercepts by zooming and tracing, you're going to find that they're the same values that you saw by looking for the intersections of the original left-hand side and right-hand side. That concludes our demonstration.